The second project I'm going to talk to you about is FOSoMo, Feature-Orientated Software Modernization. And this is based on the idea of feature location. So what is a feature? It's an end-user observed functionality. So an end-user observed functionality in Word might be the spell checker or the thesaurus, for example. And when we look at our system, that functionality is probably implemented in lots of different places. It's got a front end, so you've got to pick a menu option to find the spell checker or the synonyms. So you've got to call something in the GUI to offer you that facility. Then that GUI will call something in the business layer, and that business layer will probably call a database of synonyms. So you have code that's probably distributed over the system. Now in this case it seems fairly trivial, but when you're talking about systems that are millions of lines of code long, as Microsoft Word is, or tens of millions of lines of code long, as things like Microsoft Windows is, then that's a very difficult task. Why is that important? Well, imagine a user comes to you with a problem. They don't say, I have a problem on line 5,492,323. They come to you and they say, I have a problem with the spell checker or the synonyms. They're not working. So the very first thing the developer has to do is try and identify where that synonym functionality is in the code, because that's where the problem is. So they've got to spend time finding features. That's one scenario. Another scenario, as brought to us by our primary collaborator in this project, was the idea of re-architecting their system or changing their old legacy system into a system which is made up of services with interfaces. A service is typically a chunk of code that encompasses one functionality or a set of functionalities and provides an interface to that functionality so that the rest of the system can call it. So in our synonyms example, the service would be taking code from here, and code from here. And of course, that code, that functionality, is actually called from another piece of code as well, so it needs an interface so that the other piece of code can call the interface to use the services functionality. So while in the first scenario where you were trying to find the bug, you really just wanted to find a foothold into the functionality, here when you're trying to derive a service from an existing system, you want to find all the functionality before you can make that service. So they're two slightly different scenarios, but both are feature location. So now just an apology to those people who listened to the other talk where I also mentioned how we do our research, but I just wanted to mention it again here. It's adapted action research. Typical action research is done by participants with the goal of improving practice. So they look at their organization, they see the problems they're facing, and they reflect on how they could maybe improve on those scenarios and come up with a set of proposals which they debate and discuss, where they get people to try and knock them down, play devil's advocate, and after that they come up with a subset of proposals that are maybe refined, and they implement some of those proposals and they evaluate them in vivo. Excuse me. Sorry, so they implement some of these refined proposals and evaluate them, and that evaluation leads to further refinement of the proposals, maybe discarding of some, maybe persisting of others. But you get this iterative based approach where you try to improve practice through these iteratively refined proposals. Now obviously we're not strictly participants, we're not the software developers and software teams, but we do try and embed our PhD students and postdoctoral researchers in companies so they get a feel for the problems that are facing the programmers and the practice, how the experts maybe address these issues. So this field knowledge is then allied with what the literature says are good practices in terms of the problems the company faced. So we come up with several proposals, we reflect, discuss and debate them, play devil's advocate with them, and hopefully get to a stage where we can have confidence in some of our approaches to embody them in a tool. Once we have that prototype tool, then we can evaluate that tool in vivo, essentially evaluating the new approach and getting feedback on it and iterating towards more refined approaches, more refined tools as we go along. So our core question in terms of helping our industrial partner was, how can we advance full feature location in vivo in a legacy system where they want to move towards services. Could a JITAC-like approach help? So what do we mean by that? Well, here's JITAC, a tool we talked about earlier, which allows you to define nodes or macrostructures for your system, allows you to drag elements over onto those nodes and see the actual dependencies between those nodes. Now, if those nodes represent features, feature 1, feature 2, feature 3, feature 4, and you have pieces of code that you know are appropriate or associated with each feature, then you get a feel for where the dependencies are between those features and maybe a rest of system node, for example. And you can follow those dependencies and go, oh, well, actually that piece of code is called from here. Maybe that piece of code should belong in that feature. Maybe we could refine our feature model based on the static dependencies that are in the source code. So that was where we started. Could a JITAC-like approach help? So our objectives were really to identify expert knowledge and heuristics performing full feature location. Our industrial partner was very good in letting us observe their experts doing feature location, and using our findings from these studies and the academic literature to produce better feature location approaches and prototypes that can accommodate legacy heterogeneous systems, so maybe COBOL-based systems with domain-specific languages in them. And in doing so, to explore something that hasn't really been explored before, interface-driven approaches to feature location. So not focusing on the contents of the feature, but focusing on the interface that the feature has to offer. So I mentioned that we were able to study experts doing it manually, and we noticed a few things about them, that they were well capable of finding a foothold, typically in under a minute. So they'd find a foothold into the feature in under a minute. Their problem was finding the complete feature, not the foothold into the feature. They typically worked out from that foothold using the static dependencies, the calls, the data accesses, but they had difficulty keeping track of where they were, particularly between sessions. So if someone interrupted them, they went back to it after a tea break or a lunch break, they forgot if they'd visited a certain file or code, and they went over where they had been before. They had a large focus on location, files, directories, naming conventions, not so much the source code lexicons. A small amount of time was spent at the source code level, so they were focusing on large grain things like files and directories, and the naming conventions of those files and directories, and containment, the location of files in directories. So they mostly worked at large granularity. We also got some input from the literature. It seemed that it was very hard to have high recall unless you had some sort of manual intervention. So we like this iterative refinement approach idea that Kastner et al. Proposed at TSE 2014. We also noticed that the literature, more recent feature location techniques were where several were used in combination. So whatever tool we should try to develop should allow for several of those feature location techniques at the one time. So this is the sort of concept we came up with for our tool. You have the system elements down here, the methods, the files, the folders, and because experts are easy at grabbing, are good at grabbing a foothold, we allow them to drag from that rest of the system up here to say this folder perhaps, or this file is part of the feature. Once they do that, other elements will be dragged up to here and to here. Specifically, if an element called that folder or that file, then it will be dragged up there. If this file called other elements, then they'd be dragged here. Okay, so these are the in dependencies to the feature, and these are the out dependencies. So these are sort of ones you might consider looking at, and maybe a programmer would then drag other elements from here or from here into the feature, which would again involve updating this view and this view. You'll notice that in both views there's a certain shade that's darker, and basically that darker section says, well, we recommend you look at all these, but specifically these. Why specifically these? Typically because they have greater connectivity with what's already in the feature than the rest of the system. So that's a variation on Robillard's algorithm. Again, you can see the demo of the resultant Flints tool on this web link, but you can also see it on the Tools tab on the website. Here you see the feature, the graphical view of that, Project Explorer, which allows you to drag stuff onto the feature. Once this view gets populated, you see the in dependencies here, the out dependencies here. The bolding reflects Rob Ballard's algorithm, so these are highly connected with this and less connected with the rest of the system. And we also allowed the programmers to cross out stuff they'd studied and discard it so that you couldn't see, so that you could track where you were. Findings from an evaluation study with the tool showed that the software engineers, the experts, did indeed need little help in obtaining feature footholds. They found them very, very quickly. They largely use one-step static dependencies. Sometimes they used two steps. Sometimes they used in dependencies of out dependencies. So that was a bit of a variation, but always using static source code dependencies. Two participants used the keeping track of study dependencies facility, the cross-out facility, and they used it extensively. The participants predominantly worked at file or folder and recognition level, only going into source code less than 10% of the time, and that percentage of the time their think aloud suggested that they weren't always focused on the source code even when it was up on screen. And the Rob Ballard based algorithms seemed to help. People seemed to take more of these files into the feature than these files in the end. Well, we only had a very small number of participants in the manual study and in the tool evaluation study. I think there were 3 in the manual study, there were 5 in the tool evaluation study, and we didn't control for feature complexity or anything like that. We did notice that there was 1 in 3 improvement in the time taken. The people using the tool did the task to what they considered a satisfactory level in 1/3 the time of the people who did it manually. In terms of potential future improvements, the evaluation suggests that we look at finer granularity data dependencies, field level data dependencies, that we look at containment in folders, that we make several small user interface refinements, which we will do, and we have explicit process guidelines for tool usage because it is quite a complicated tool to use. We're also going to put in another textual-based feature location tool in there. Textual means that it compares the words in the query for the functionality, like synonyms or thesaurus, with the words that appear in the source code, the variable names, the method names, the class names, to see the method names and classes or files that seem to be aligned with that query. You'll notice we also have another tool available on the website, Fusix, and this is an interesting tool. It's a bit more exploratory. The problem with textual-based techniques is that you're comparing words in the query with words in the source code, and there aren't that many words in the source code that are meaningful. Just method names, class names, variable names, field names, and maybe the odd comment. So that's called the word paucity problem, that there isn't many words to compare to the query. So we're looking for ways to enrich the words we're comparing. So one source is the VCS, where we can look at the commits that have been applied to the source code. So here we have commit 1 and the description associated with commit 1, what commit 1 does. And you'll see that commit 1 is associated with folder or file A1, let's say file A1. So now we have a description associated with A1. In fact, we have 2 descriptions associated with A1. We've 2 descriptions associated with A2, 1 description associated with AN. So now we can say that the words associated with A1 are the descriptions here, the words associated with A2 are the descriptions here, the words associated with AN are the descriptions here, and those descriptions are a bit more verbose. They give us more words to compare against the query. And that's what's happening over this side. We make a document for each file in the system, and we have the terms from the descriptions of the commits. So for document 1, which refers to A1, we have the descriptions from commit 1 and commit 2. And that then becomes the IR engine's raw material to compare with the query. The results were quite impressive. Specifically, it showed that certain types of systems responded really well to this scheme of things, other types of systems not so well, and we could maybe start characterizing the systems to see whether this technique or a more ordinary technique which just relies on the words in the source code should be applied. But when we combined this technique with the original technique where we just look at words in the source code, we got much better performance than just using the words in the source code over all 8 systems that we tried it on. So that's an interesting technique that we'll be pursuing as time goes on. So deliverables to date in this stream, it's a more immature stream than our ARC recovery work, architectural recovery and consistency work, but we have had 2 Zerocon papers on reflection modeling based feature location, and we've developed a prototype. We have an ICPC conference paper on the manual study with experts that we carried out, a Saner paper on the Fusix approach. We have various implementations. We have a substantial prototype FLINS that is based on static analysis of heterogeneous systems, both invocation and data dependencies. We've design principles gleaned from the initial study. We've reviewed the feature location literature to provide more design principles, and we've ROBL-based feature location support embedded in the tool, and we're on our 2nd iteration of that tool. The availability of the refined prototype is on the company. It's in 7 desktops in the company, and we have a prototype video that you can see on the website, and we have successful Lero 3 funding from Enterprise Ireland, Innovation Partnership funding, and from Lero 2 ARC funding.